Hey folks, welcome back to another lecture from the Introduction to Earth Sciences lecture series. I'm Dr. Matthew Wielicki. Please follow me on Twitter at Matthew Wielicki. This is going to be a lecture about earthquakes. We've talked a little bit about how the universe and our solar system formed, a little bit about plate tectonics, and then we went into minerals and our rock types, and we've talked about volcanoes. And we will now be kind of shifting gears into talking about processes that exist on the surface of the Earth, for example, earthquakes, eventually mountain building. And we'll talk a little bit about how we date rocks in deep time, and then we'll move into the hydrological cycle and talk a little bit about mineral resources as well. And this is an image in front of you of about over 4,000 years of significant earthquakes. And one thing that I think you can notice right off the bat is it doesn't look like a shotgun pattern. It's not a random pattern. There tends to be these distinct zones where we have lots of earthquakes. And what we'll see as we get into it, that earthquakes occur where plates are usually grinding past one another. With anything in nature, it's not a perfect rule of thumb, but it's in general, it's pretty good, and there's always some outlier events that we'll discuss that we think we understand why they're occurring. But for the most part, the earthquakes tend to concentrate along the plate boundaries where these large, massive lithospheric plates are grinding past one another. Have you guys ever experienced an earthquake? If you grew up anywhere besides the western U.S., if you're in the U.S., it's likely that you didn't. I grew up in Fresno. That's about in the center of California on this map. And the first earthquake I remember was called the Loma Prieta earthquake in 1989. And I was a Giants fan. I was excited to watch the Giants battle out with the A's of the Battle of the Bay for the World Series. Unfortunately, we got swept 4-0. But during one of the games, as they were announcing the players, the screen started to crackle and the camera started to go in and out, and I could hear the announcers start to talk about that they were experiencing an earthquake. There was a 6.9 magnitude earthquake. It was about 50 or so miles away from, the epicenter was about 50 or so miles away from San Francisco, where Candlestick Park was, where the World Series was being played. And it caused a significant amount of damage. I didn't realize it, but Fresno, where I was at and growing up, was also shaking a little bit. I couldn't really feel it. And I looked out into my backyard where we had our pool, and the pool was sloshing. The water was going in and out. And so it was clear to me that there was actually shaking going on. It was on the edge of where you could actually feel the earthquake, so I didn't really feel anything. But it was clear that those waves were traveling all the way to Fresno. So that was my first experience with an earthquake. And so California is right along a plate boundary. And so California has quite a bit of earthquakes that occur, very different than, for example, the quieter plate side, which would be the eastern, southeastern edges of the U.S., although we'll talk about some interesting exceptions in those areas as well. We're living in an era of pretty large earthquakes. We don't totally understand why that is, but in the last 2 decades or so, we've experienced 3 of the largest earthquakes ever recorded in the history of these records. These records don't go back too far, but since we've had a good seismographs and seismometers that we'll talk about in a minute, we've had pretty accurate recordings. Before that, we had to kind of use qualitative methods as opposed to quantitative methods because we didn't have sensitive instruments to measure these things. But it appears that these last 2 decades have been very active in terms of large earthquake activity. And so there's some competing hypotheses about why that may be. But it's just an interesting fact, and we're going to talk a little bit about both the 2004 Sumatran earthquake and the 2000, which is called the Boxing Day earthquake, and the 2011 Tohoku earthquake in Japan, as well as a little bit about the Haiti earthquake there on the left, the 7.0 in 2010. We're going to compare and contrast those. Well, let's define an earthquake before we get any farther. So it's a very simple definition. An earthquake is an episode of ground shaking. I like to use this image on the right. You think about holding a pencil in your hand, and as you try to break that pencil, what happens is that pencil will deform and it will bend a little bit. And then when it breaks, you don't end up with 2 curved pieces. You end up with 2 straight pieces. And if you could watch right at the break point, what happens is the pencil kind of vibrates and rebounds back to its straight position, because as you were breaking it, you were bending it, but it naturally wants to come back to that straight position. So there's a little bit of vibration that works there. And that's essentially how an earthquake works. To be a little bit more specific, we could define it as a ground shaking that is caused by a rapid release of energy. We call that energy strain. And so this energy moves outward in spherical waves in every direction. The energy can be measured all the way around the globe. In fact, we'll talk a little bit about in a minute about how earthquakes help us to image the interior of the earth. We don't really have very good evidence of actually sampling the deep earth. In fact, the deepest borehole ever was done by the Soviet Union in the late 70s, which got down to about 12 kilometers or so. And so we haven't really been able to sample very deep into the earth. There's natural methods that will bring up deeper rocks in certain areas. But in order to start to image the deep earth, we have to rely on these proxy methods like the energy and the waves that are being released from earthquake events. They occur every day. There's more than 1 million of these detected every year. That number keeps going up as we put more and more remote equipment out, and we put equipment along the ocean floor. Many of the plate boundaries are along the ocean floor, so these are earthquakes that we were tended to miss until we could have these types of technologies. And the vast majority of this is a release of built-up strain due to stresses of the plate tectonics primarily, and usually breaking along a fault. Some of the hazards that we'll talk about are obviously ground shaking, but the truth is the ground shaking doesn't really cause a lot of loss of life. If you're out in the open and the ground starts to shake, it's really impossible for the ground to shake violently enough that it could hurt you. It may throw you off balance. You may have to get down on a knee or even maybe sit down because the shaking can be so violent, but rarely will anything actually happen to you if you're out in the open. But if you are in places where there is buildings and infrastructure, it's really the buildings and the infrastructure that can collapse that causes a lot of the damage. We'll end with a couple slides about some of the engineering practices that have really helped to mitigate that. Tsunamis are a big hazard associated with earthquakes, landslides, disease and starvation. So that tended to be what caused a lot of loss of life in Haiti during a recent earthquake there. Liquefaction, that may be one that you're not familiar with. So that's an image of liquefaction there in front of you. That's from Christchurch in New Zealand. After an earthquake there, what happens is some of the roads were still built, were not paved. They were just dirt roads and kind of sand roads. The water table is pretty high. What happens is when the ground shaking starts, the water rises to the surface and it turns what used to be a solid road where that vehicle was parked into essentially a liquid. And you can see now that the ground shaking has stopped. That water has seeped back into the ground and they're standing on a solid surface again. Unfortunately, the vehicle is 3/4 buried. And also fire. That's actually what was the largest loss of infrastructure in the 1906 earthquake, was fire, not the actual ground shaking itself. Earthquakes can be very deadly. In fact, when it comes to natural disasters, they tend to be one of the most deadly natural disasters that we have. And you can see there highlighted are 2 recent earthquakes. That's the Boxing Day earthquake in Sumatra in 2004 and the 2010 Haiti earthquake. Notice the vast difference in the magnitude. One's a 9.1, one's a 7.0. You may think that between 9 and 7 is not all that big, but this is a log scale, so we'll come to this in a few slides. But that really means that it's 100 times, over 100 times stronger, the Sumatran earthquake, than the Haiti earthquake. The infrastructure in both was not very good, so there was not a lot of engineering and building regulations, and Haiti also had a pretty large outbreak of disease and starvation, which caused more loss of life. But these tend to be some of the largest natural disasters that cause loss of life. I think of this as a motivating factor to help study these things so that we can understand them better and hopefully be able to mitigate some of this loss of life. The causes of an earthquake are really 2 that we're going to focus on. They're the 2 that are underlined there because that's really the majority of the earthquakes, and that's where strong earthquakes occur. That's going to be slip on an existing fault. So where there's sliding occurring essentially along a fracture because the rocks need to be broken. Nature's relatively cheap. Nature's going to take the easy way out. If there's a fracture existing in some rocks and their stress is building up, that's where it's going to slide past one another. Occasionally those fractures don't exist, so you get formation of a new fault. We'll touch on that a little bit, but I just wanted to mention a couple others. So you can have earthquakes occur from the sudden change in the arrangement of atoms. Sometimes even during metamorphism, you can have them occur during movement of magma in a volcano. If you recall our volcanoes lecture, we talked about Mount St. Helens. They were pretty confident Mount St. Helens was getting close to erupting because there was this increase in a swarm of earthquakes. They also saw deformation on the side of the mountain. So they were pretty confident that magma was moving around below the mountain and it was moving closer to the surface, which would suggest obviously that there was a imminent eruption, and they were right. Explosions of a volcano. So an eruption the style of Mount St. Helens is so powerful that it actually sends shock waves through the ground, so you get ground shaking. Giant landslides. One that I like to think about is meteorite impacts. These would be some of the largest shaking events ever. We've never recorded a 10.0, for example, but the estimates are huge for large meteorite impacts, things that we energy release that we've never really thought of. And also underground nuclear bomb tests. So one of the ways that we know that certain countries continued to test nuclear weapons was partly from satellite photography and being able to see them mobilizing, but also when they would do these underground nuclear tests, they would send shock waves out, and those shock waves are actually unique as compared to an earthquake, because everywhere there's a compression wave that reaches first because it's literally an explosion. And so I'll show you when we talk about earthquakes that usually when you have an earthquake, you'll get compression waves in one direction, but you'll get tensile waves in another where you're actually pulling as opposed to pushing. Well, let's kind of think about this in a map view or in a 3D, three-dimensional view. When we think about an earthquake, we're going to look at a lot of little funny diagrams like this where we can imagine a fault surface that's sloping into the ground, and where the earthquake actually releases is always going to be somewhere within the earth. That's usually where the stresses are the greatest. That's where you're going to get the initial release. And so we call that the focus. So you can see that's focus A is a little ways down into the crust along this fault that is cutting down into the crust. When we put this in map view, because usually it's difficult to show images like this if you want to talk about where an earthquake occurred, we usually put it in map view, which is looking down on a map. And then what we're doing is we're projecting directly up from the focus onto the surface of the earth, and we call that the epicenter. So the actual earthquake is occurring somewhere below each of these red dots down into the crust. And this is a picture of the southeast US. Notice that there's a couple hot spots. We're going to talk about the New Madrid seismic zone. That's actually where one of the largest ever recorded, well, not recorded, but reported earthquakes occurred in 1811. This is an interesting area that we'll touch on, but it's estimated that it was an 8.1. Obviously, we didn't have the sensitive equipment to actually put a quantification on it, but there's reports of the Mississippi River flowing backwards. So here's some of those terms. The hypocenter, or the focus, that's the point below the surface where the earthquake is actually releasing. If we project directly up to the surface of the earth, we call that the epicenter. That's the term that you're probably used to seeing when you see earthquakes being reported. Just remember that the earthquake is actually releasing somewhere below that dot, and it's releasing along a fault, which is a fracture or crack in the earth's surface. That's where the sliding is going to occur. Some fault basics are going to be dependent on the stresses that are occurring due to plate tectonics. So remember, in plate tectonics, we talked about 3 different plate boundaries. We talked about divergent plate boundaries. That's when the crust is pulling apart. So the fault type that you get in a divergent plate boundary is in the upper left. That is known as a normal fault. One way to think about these things is to draw a little person across the fault and notice where there's a hanging wall, or I like to call a head wall, and also a foot wall. And then if I like to remember the acronym FUN, foot wall up normal. If the foot wall is going up, that's a normal fault. One of the other plate boundaries that we had was a convergent plate boundary. So that's the pictures on the upper right and the lower left. Those are both, notice the arrows on the sides, those are converging, the plates are coming together. And what we get there are reverse or thrust faults dependent on the angle of the fault. If the angle of the fault is very steep, we have a reverse fault. If the angle of the fault is relatively shallow, we have a thrust fault. If there's no divergence and convergence, our last plate boundary we call transform, where the plates are sliding past one another, which we call shearing. When we have shearing, we don't have what we call a dip-slip fault. So the first three that we just talked about, they have vertical motion. We call those dip-slip faults. We have what we call a strike-slip fault because there is no vertical motion, but there's still a fracture. The rocks are still sliding past one another. They're just doing it horizontally as they slide past. We'll look at these a little bit more in detail. So here's our example of a normal fault. Remember the acronym footwall up normal. This is a result of extension or pulling apart. If you think about the surface of the earth in this diagram, the surface is actually getting longer because now there's a scarp that's exposed. And so the two green patches on the surface are actually pulling apart, right? They're diverging from each other. This is what it actually looks like in nature. You have these multiple normal faults and you get what we call horsts and grabens. If you've ever driven in the Southwest and you're driving from Salt Lake City to San Francisco, for example, you'll notice that as you go through the basin and range, literally the name comes from these figures and this type of configuration. The basins are the grabens. These are these drop-down blocks and kind of go into a valley, and then you'll go over this linear mountain range, and then you'll drop down into a valley. Those are the horsts, and that's why we call it the basin and range, is because we have these linear mountain ranges in between and then valleys in between, and that's because there's been a lot of extension and pulling apart that has happened in the the western U.S. and the southwestern U.S. Over the last few tens of millions of years. Here's what it looks like in nature. There is these two nice normal faults. If you had to take that gentleman and put him along the fault on the left, you would see that the footwall was going up. If you moved him across the fault that's on the right, you would also see that the footwall is going up. So these are two normal faults. If we have the reversed type of configuration where the plate isn't diverging but it's converging, we get what we call reverse and thrust faults. And again, these are going to be dependent upon the steepness or the shallowness of the fault itself. But notice the arrows, this is coming from compression or squeezing. The actual green patch on top is now getting a little bit shorter. They're coming together because you have this overhang that's occurring. So you're actually shortening the block as opposed to lengthening it like we were before. The image on the right is from Utah where you can see a nice reverse fault. This tends to be associated with mountain building because notice you're pushing one of these blocks up over the other one. So where we have mountain ranges like in the Grand Staircase of Escalante National Monument, you get quite a bit of these reverse faults. The final fault type that we'll talk about, and we're going to come back to this in the next lecture when we talk about mountain building, is known as a strike-slip fault. And this is where the blocks are literally sliding past one another, and there's no vertical motion, but there is a fault surface. That fault surface is nearly vertical. This is an example of a strike-slip fault in the Central Valley in California where I grew up. You can see these rows of crops after an earthquake occurs along the San Andreas Fault, and they are all offset. They're not moving vertically. The field is still relatively flat, but there's an offset in one direction or the other. When the earthquake occurs, the motion along the earthquake we call displacement. So that's going to be the offset, the amount of movement that occurs along the fault after the earthquake occurs. The image on the left there is from the 1906 earthquake. This is from a field near San Francisco where the fence was definitely distorted. There was this S-bend in the fence for a while, and after the fault it clearly had broken, but now you can see two straight pieces again. And between those two posts where it broke, that was the amount of motion on the fault during the 1906 San Francisco earthquake. If there's vertical motion, what occurs is that a fault scarp is created. So we don't get fault scarps and strike-slip faults like you saw in the last image. But if there's vertical motion, then we will get a fault scarp where you can see that the blocks of land are moving vertically next to each other. There's up and down motion, which you don't have on strike slip faults. So how does a new fault form? Well, let's just imagine that we have a block of wood between two metal vices or a block of rock between two metal vices, and we're moving those metal vices in opposite directions. At the beginning, not much is going to happen, but eventually we're going to start to get these little tiny small cracks, and we're going to start to deform the rock a little bit. It's going to be on a very small scale because rock is relatively brittle, so the images here are definitely a little bit distorted so you can see it better. But at some point, we're going to have deformed the rock so much that these little hairline fractures are going to start to line up, and you're going to get a big rupture. And what's going to happen at the end of that big rupture is we're going to be left with two straight pieces of rock. Very analogous to the example of breaking the pencil we talked about before. The forces from the metal vices, those two red arrows along the metal vices, we call that the stress. That's going to be the force being applied, the push, the pull, the shearing, the sliding past one another. And the deformation in the rock, the fact that it's changing shape a little bit before it actually ruptures, we call the elastic strain, right? That's the change of shape, which disappears instantly when the stress is removed. That's why it's called elastic, right? We call an elastic rubber band elastic because as we stretch it out, we let it go, it comes back to its original shape. And so the stress is the force applied, and the strain is the change in shape or the deformation. Usually what's going to happen is that faults are going to be, or earthquakes are going to be occurring along pre-existing faults. This is an image of the San Andreas Fault that runs up and down the western U.S. This was the earthquake of the 1989 Loma Prieta earthquake that I experienced as an 11-year-old in 1989. The reason that the stresses build up until they eventually release is because of friction. If the fault was infinitely lubricated and smooth, then you would never actually build up the strain that gets released because the stress would just be accommodated all the time. You just constantly have these tiny little slidings past each other. You probably wouldn't even notice it. But because these are made out of rocks and rocks are rough surfaces, there's a lot of friction. And the plates continue to move, but these faults kind of stay locked up because of friction. That's the force that's resisting sliding on the surface until you eventually overcome it and you get the earthquake itself. Right? And that's essentially how an earthquake is generated. So you have slip on a pre-existing fault, which causes the earthquake, but the slip is occurring because the faults are weaker than the surrounding crust. There's already a fracture that's existing, and over time they're building up a lot of this strain and stress. It's building up, the forces are continuously being applied. Because the fracture has friction on it, it's locked for some amount of time until it can't overcome that force anymore, and then that friction lets go and you get sliding. We call this stick-slip behavior. The stick part is the friction part, and the slip part is when the friction is overwhelmed and you get sliding. You can imagine that like having a brick on a table and a spring attached to it. As you start to move your hand away continuously at the same slow rate, what happens at the beginning is that the spring starts to extend. Right? In that second image, you can see that the spring is extending, but the brick hasn't moved. At some point, the spring's force on the brick is going to overcome the friction of the brick on the table. When it does that, the brick is going to slide towards you a little bit. And as it does, it's going to compress the spring, and it's going to relieve a lot of that force that you're putting onto it. As you keep pulling your hand back continuously, you're going to start to stretch that spring again. It's going to overcome the frictional force between the brick and the table, and it's going to slide again. This is a graphical representation of this stick-slip behavior. So this is overcoming the friction, having movement, which we call displacement, and then eventually the stress starts to build up again. That's a simplistic way of putting into words what eventually became known as the elastic rebound theory. right? This is the concept that earthquakes occur when rocks start to elastically bend, eventually fractures. That fracture generates an earthquake and releases energy that decreases the elastic energy that's stored, and we kind of repeat the process as the plates continue on their motion. If you remember from the lecture 2 about plate tectonics moves at about a continuous rate depending on which plate boundary you're talking about, and it's on the order of 5 or so centimeters per year. That's about the speed that your fingernails grow, and so these plates are continuously moving, and even once you release some of that strain, it starts to build up again over time, and that's when you get another of these earthquakes. The elastic rebound theory is really the theory that describes the origin of earthquakes. It was developed after the 1906 earthquake. There was a report, the San Francisco earthquake, there was a report done that really started to identify that there's a lot of deformation that's going along these faults, and it's continuously changing over time, and eventually it overcomes the friction on the fault and releases. Very analogous to the energy that is stored when you're breaking that pencil, because it bends first, that energy being released when the pencil finally breaks, and the little individual pieces of pencil vibrating back into being straight pieces. When earthquakes occur, they tend to have other events either before or after them. Unfortunately, it doesn't happen before very often. What happens is we usually get the main shock as the first shock. You'll see that that's going to come into play in terms of prediction purposes. But if there is an event before the main big earthquake occurs, we call that a foreshock. So that would be a series of smaller earthquakes that precede the major earthquake. But usually what happens when we have a big event is we always have aftershocks. And the aftershocks are a series of smaller earthquakes that follow the major earthquake event. You can imagine how much these can dampen rescue efforts when buildings and infrastructure is already damaged. Rescuers are inside trying to find survivors, and the ground starts to shake again. It's a very difficult situation when you're trying to rescue people from damaged infrastructure. But unfortunately, we don't get a lot of foreshocks, but we always have quite a few aftershocks, especially if the event is pretty large. And that's just because when the event occurs, part of the fault breaks, but then it pushes energy into other parts, and so everything has to accommodate over some amount of time, and these aftershocks last for months, if not years, after a big earthquake. Earthquakes release energy through seismic waves. So seismic waves are the actual energy that's being produced. They travel in all directions from the focus where the earthquake actually occurs, and they come in two essential flavors, body waves and surface waves. They're analogous to dropping a pebble into a pond. You drop a pebble into a pond and you'll see that you create waves. They are hemispherical waves going out in every direction along the surface, and you can see in this image that they start to dissipate as they go away. We'll see that a good chunk of the damage that's done from an earthquake depends on how close you are to the actual epicenter, because the waves dissipate. Here, where I am currently in the southeast in the United States, if there was a big earthquake in San Francisco or Los Angeles right now, I would have no idea because I'm far enough away that the waves would have long dissipated prior to them reaching me. Now, we will be able to pick them up on sensitive equipment that we'll talk about in a minute, but a human wouldn't actually be able to feel it, and there would be no damage done to any infrastructure. So seismic waves come in two categories, body waves and surface waves, and then under each of those, there are individual types of waves dependent on their motion. We're going to talk about each of these individually. So let's just define again what body waves and surface waves are. It's pretty simple. Body waves travel through the center of the Earth, the body of the Earth. They do not travel along the surface. They're going to come in two types of waves that we call P and S waves. And surface waves are traveling along the interface of the surface of the Earth and the atmosphere. They are going to come in a couple flavors called L waves and R waves, and we're going to talk about this data plot that you see here in the lower right in a moment. So let's talk about the body waves individually. The first type of body wave, which is also the first wave to arrive because it has the fastest velocity, we call the primary wave, as it is the primary wave to arrive. This is a compressional wave. You can think of this as pulling a slinky apart and giving it a little push, and you'd see that the slinky wouldn't be moving up and down or side to side, but that the individual coils would get closer together and that wave would progress through. That's what we call, or what we mean by a compressional wave. The particles are actually squeezing and then releasing. So there is no motion in terms of up and down or side to side, but there is a actual density change as the wave passes through. The particles push together, the density goes up, and then they release. This is the fastest wave, thus it arrives first, and it's known as the primary wave. It travels on the order of 8 kilometers per second. That's something like 18,000 miles per hour. It's not very destructive because it's a body wave and it's traveling through the Earth. But one important thing is that it can travel through both solids and liquids. The other type of body wave is known as an S wave or a secondary wave. This is a shear wave. This has a up and down motion, kind of analogous to what you'd think about when you think about ocean waves. This up and down kind of rolling motion. Think about holding a string and giving it a little snap, and you'd see that there would be this down trough and then this crest in the front. These have moderate velocities. They travel about 60 or so % of the P wave speed. They are also not very destructive because they're traveling through the body. But one important thing is that their body of the Earth. One important thing is that they travel only through solids. And so you're going to see that this is actually the evidence that we have for having a liquid outer core. The P waves travel faster than the S waves, and so they're the first to arrive. And what we'll see is that that will be important in terms of measuring the distance. We'll call that the P and the S wave. The velocity waves, they vary, and as they travel, it depends on the type of rock and their sediment. But in general, the velocities of the P waves are about 2 times as fast as the velocities of the S waves. It is the fact that P waves travel through liquids and solids that led our understanding of what our inner core looks like and our outer core. And what we noticed is that this was noticed in the early 20th century, that there was what was known as a P wave shadow zone. And this was a shadow zone that was occurring because as the P waves, although they could travel through liquids, they traveled at very different velocities through liquids than they do through solids, because the compressibility of a liquid is very different than a solid. And you know that by that a P wave is a compressional wave. And so they very early in the 20th century, there were these shadow zones that were observed. And the one that led people to think of the outer core as being liquid was the fact that anytime there was a large earthquake, there was essentially no S waves on the other hemisphere of the globe. And it didn't really matter where it was, and that led scientists to believe that the outer core was in fact liquid, and that the core is spherical because no matter where the earthquake occurred on the surface, it was always about the same size on the other side of the planet that we saw the S wave shadow zone. And that suggested to scientists pretty early on in the mid 20th century that there was a solid inner core surrounded by a liquid outer core. All right, let's move on to talking about surface waves. So surface waves are the waves that are traveling at the interface of Earth's surface with the atmosphere. They come in a couple flavors. The first one is an L wave, or named as a love wave, named after the people the scientists that discovered them. These are seismic waves that cause the ground to essentially swing back and forth like a snake almost. These are very destructive waves, primarily because they're occurring at the surface. Body waves, as they travel through the center of the Earth, they don't really bump into any infrastructure that we have because we build along the surface. So these are very destructive waves, kind of with a snake-like motion. The other type of surface wave is known as an R wave or a Rayleigh wave. And this is much more analogous to the S wave, body wave, where you have this up and down kind of rolling motion. But remember that both of these are occurring at the same time. These are also very damaging. You can imagine a building being jolted up and down, but they're not as damaging as L waves. It's very important to remember that the distance from where the earthquake occurs, that we call that the focus or the hypocenter, is really going to dictate how much energy you're going to feel, because the seismic energy essentially dissipates as it travels through the earth, just like the picture of the pond or the pebble falling into the pond. The waves farther away from where the pebble actually hit the surface are much smaller than the waves right at the surface. And so the same thing happens as the waves travel away from the focus, they start to dissipate. And so when we start thinking about damage and hazards, one thing that we're going to always be thinking about is how close the area is to the epicenter or the focus. We talked about the causes of earthquakes. We focused on the upper two, but one thing that we didn't talk about is an earthquake from an SEC football game that you can see there at the bottom. This was in 1988. This was a game between two competing SEC rivals, Auburn and LSU, and the stadium on the campus of LSU is actually very close to the geology building. You can see those kind of labeled there in that image at the bottom. That's known as the Stevens Building. And in that geology building at the base, in the basement, to kind of dampen vibrations from trucks on the surface and things like that, or elevators moving around, in the basement was a device that would record ground shaking. And on that day in 1988, LSU came back in the fourth quarter to score a touchdown and win 7-6 at home. And when the scientists got back into their office after that game on the next Monday, they noticed that they recorded something. And this became known as the earthquake game. So this is the seismograph on the upper left. That's the instrument, sometimes called a seismometer. We'll define that on the next slide. And that what is actually spit out from that is known as a seismogram. And that is the seismogram from October 8th in 1988. And you can see that right around the time of the earthquake, there was this intense episode of shaking as everybody started jumping up and down in their seats. And because the geology building was so close and you have 100,000 or so people jumping up and down rooting for their home team, it was actually recorded by the instrument. So this is just a way to introduce these instruments. We call these seismographs, sometimes also seismometers. This is all digital now, but this is essentially how they were made back in the day. You have a drum, and that drum is rotating, and it has a needle on it that's creating a line. If there's no movement at all, you have a very straight line. But if there's movement, the drum is anchored into the ground and the needle is on a spring. So as the ground starts to move, the spring helps to dampen the needle a little bit, but the drum starts to shake up and down. And what that translates to on the paper is that your straight line starts to wiggle quite a bit. And this is the resulting data that we get from these big drums. And this is what we call a seismogram. This was the record that we just looked at from the earthquake game. And this is how we can start to quantify earthquake shaking, as opposed to what used to happen, which was much more qualitative analysis of earthquakes, looking at damage, interviewing people. We'll touch on that here in a minute. There's quite a few advantages of using seismographs that produce seismograms. First of all, they can automatically record an earthquake. So if you're in a rural area where there's not a lot of people, now you could put these things out and they would actually record the earthquake. They can actually detect motion that we can't sense as humans. They can tell us that an earthquake is actually occurring because we may not be able to sense it. But two really important features are that they can tell us where the earthquake occurred, and they can tell us something about the intensity of the earthquake in a quantifiable way, as opposed to a qualitative way, which is much more subjective. So we're going to focus on these last two. So let's say you have an earthquake. Well, what's going to happen is when that earthquake ruptures, and it's going to rupture at the focus or the hypocenter, and if you project directly onto the surface, you can see the epicenter there labeled. As those earthquake waves are going to travel to these three imaginary stations, the P wave is going to start to gain ground on the S wave. And the farther they go, the farther the P wave will be able to gain ground. So the gap between the P wave and the S wave starts to grow the farther you go away from the epicenter. And so what you can do is you can look at these three imaginary stations. You can look at their seismograms. Here they are from stations 1, 2, and 3, and you can measure what we call the P and S wave gap. So you measure what time the P wave arrives, what time the S wave arrives, because those are your first two waves. They'll be before the surface waves arrive. And the time difference between those two tells you something about the distance. So here we have some imaginary times: 3 minutes and 19-second gap, a 5 minute and 38-second gap, and a 7 minute and 35-second gap. What you can do is you can go to certain plots where we estimate how fast the waves are traveling through the surface of the Earth. And you can use those plots to estimate that station 1 must be about 2,000 kilometers from the epicenter, station 4 must be, or 2 must be about 4,000 kilometers, and station 3 must be about 6,000 kilometers. But you don't know anything about direction. All you know is that from station 1, you draw a circle 2,000 kilometers away, and along that circle somewhere, you have an earthquake. But if you have 3 of these stations, you can essentially triangulate. And you can triangulate station 1, 2, and 3. You can draw your circles, and your circles should intersect at essentially only one point, all 3 of them. And you can see that by doing that, you could have identified that the earthquake happened somewhere in eastern Colorado, for example, in this image here. So seismographs made it much easier to start to use numbers to quantify and identify where earthquakes occur. If you're an emergency response team and you're trying to get to a place where there was an earthquake, this is very valuable information, because usually if it's a large enough earthquake, the infrastructure for people to reach back out, cell phones, internet, communication lines, those get destroyed. And so if you have this information from farther stations where you don't really feel a ton of shaking, you can start to pinpoint exactly where you should start spending response units. The second important thing about seismographs is they tell us something about the intensity. Before we had a quantitative method to measure earthquake information, we relied on what we called the Mercalli intensity scale. So this is an Italian scientist by the name of Giuseppe Mercalli. He developed this because they wanted better information about how big earthquakes occur and where they occur. And this scale goes from 1 to 10, and it essentially is a subjective or qualitative way of identifying how much shaking and damage there was in an earthquake. The damage you can go out and visibly survey and identify. Again, remember, the closer you are to the epicenter, the more damage you should observe, because the greater the shaking. And then you also interview people, but you can imagine that some people have very different experiences. Somebody says, well, yeah, it kind of rattled me a little bit, but I went back to fell asleep. And somebody else could be like, oh my gosh, I thought the world was going to end. So it's a very subjective way of trying to identify earthquakes. In the 1906 San Francisco earthquake, it was all we had at the time, because these seismographs had not been invented yet. And this is how we estimate the shaking that occurred. So it's put onto this Mercalli intensity scale. You can see that the warmer colors tend to be surrounding the San Francisco Peninsula and north of that. And then they get cooler as you go away. The estimate is about a magnitude 7.8. We'll define what that is in a moment. But we really don't have any quantitative data for the 1906 earthquake. It was the Mercalli intensity scale was used. Something that you should notice on the picture on the right is that the San Francisco Peninsula is rather small. It's only about 7 to 8 kilometers across, but there was a relatively big difference in terms of the shaking, where we have 6s, 7s, 8s, 9s, and 10s all within a few kilometers of each other, and that's really due to what the subsurface is made of. If the rocks below the buildings are made out of things that are prone to shaking, then they actually shake dramatically more than areas that are a little less prone to shaking. Eventually, in the mid-20th century, we start to really get these seismographs and seismometers online, and a gentleman by the name of Charles Richter comes around and develops what we call the Richter magnitude scale. And this is usually what you'll hear reported when you see news reports in numbers from 0 to 10. And what we see is that what Richter developed was he wanted to quantitatively figure out how much shaking occurred. And so he was going to use the data from the seismograms as these instruments are coming online. Again, they're all digital now, so they don't look like they do in the picture that you see there on these drums, but they're essentially doing the same thing. And he figured out that if he can measure the P and S wave gap, That's the time, again, difference between the P and the S wave. Remember, that's going to tell you something about how far away the earthquake occurred. And he measures the amplitude of the largest wave. He can use those two to essentially predict what the magnitude was, or to develop a scale that works with those two numbers. And essentially what you do is you put it on a plot. You plot on the left the S and P wave time. Up there you can see it's something like 25 seconds. And then you plot the magnitude of the amplitude of the largest wave. That's 23 millimeters. And you go to one of these plots that Richter developed, you draw a line, and where it crosses the center line, the B line in the center of the column, that's the magnitude that you have, which is a magnitude 5 in this example. Something to note is that we brought up a little bit ago when we were talking about the Japan and the Haiti earthquake, the Sumatra and the Haiti earthquake, they were a 9.1 and a 7. I mentioned that that's actually 100 times more powerful. The Japan earthquake was 100 times, or the Sumatra earthquake was 100 times more powerful. That's because the Richter moment magnitude scales are logarithmic. They're on a log base 10 scale. That means for every change in the Richter magnitude, you have 10 times the amount of shaking. It's 10 times stronger. So if you have two numbers, it's 10 times 10. So the difference between the 7 that occurred in Haiti and the 9.1 that occurred in Sumatra is essentially 10 times 10. And so it's 100 times more powerful. People think that the Richter scale is linear, and thus a 9 is just a little bit stronger than an 8 and a little bit stronger than a 7, but it's actually 10 times stronger than an 8 and 100 times stronger than a 7 and 1,000 times stronger than a 6. So where do earthquakes occur? So we'll see that the majority of earthquakes, as we talked about in the very first slide, occur along plate boundaries, all three of our plate boundaries. But there's going to be a couple extra spots where we have earthquakes that occur that we'll touch on. So divergent plate boundaries have a host of earthquakes. They have transform or strike slip faults where the divergent lines are kind of offset. You can imagine those two divergent plates right there in the image on the left, and they're kind of offset a little bit. So where they're spreading, there's a little section where the spreadings are offset, and that means that in that area the faults are actually sliding past one another. And then in other areas where you have this divergence, you're going to get our normal faults. These are both going to be associated with shallow earthquakes. Where we have convergent plate boundaries, we have a whole host of different types of earthquakes. We have shallow earthquakes, intermediate earthquakes, and deep earthquakes. That's because we're taking a rigid plate. In this example, there's an oceanic plate. It's being subducted underneath that volcanic arc, that little bit sliver of continental plate, and that whole lithosphere is being shoved down into the mantle, and it can cause earthquakes essentially all the way down to about 700 kilometers. And then around 700 kilometers, something very interesting happens. The plate gets so warm that it no longer can build up the stress and the strain that's needed to actually fracture and create an earthquake. It's going to bend and ooze and become a little bit more gooey, like dough or silly putty, and you can't really build up those stresses to make it break. So because of this temperature increase, we see that our earthquakes essentially stop right around 700 kilometers or so. Where we have transform plate boundaries, we're going to have strike slip faults. These are going to be shallow earthquakes sliding past one another. We're going to come back to these a little bit more when we talk about mountain building. A couple unique situations that are not totally associated with plate boundaries at the moment, but will be soon, is where we have divergence occurring on a continent. We call these continental rifts. So at the moment, the Horn of Africa is pulling away from mainland Africa. In fact, I used to live just on the edge of the Horn there in Somalia, in Mogadishu, in 1986. I went to second grade in Mogadishu. It was a sister city to where I grew up in Fresno, California. We had these sister cities in the 80s, and my parents went over there to help develop an information system for the airport, the international airport. At the time, it was very safe. I had a great time. And I actually had a chance to go out into Kenya and see some of this Rift Valley, the East African Rift Valley. It was spectacular at the time. I didn't really know what I was looking at as a second grader. But now looking back, I stood along some of these big faults and some of these big volcanoes that exist because the Horn of Africa is pulling away. And eventually, in a few tens of millions of years, there'll be a shallow sea That's separating the Horn of Africa, which will now be an island, away from mainland Africa, very analogously to Madagascar, which if you look in the inset image of the globe, that's the island that is pulled away from the southern portion of Africa. It'll be very analogous to that. There'll be a sea now in between them. So this is divergence that's along a continent. Another example is collision zones where two plates are crashing together. This is, for example, the formation of the Himalaya. This is where the Indian subcontinent slams into mainland Eurasia and southern parts of Asia. And because these are two continental plates, these are both felsic rocks, low in density. Neither of them want to be subducted, and you can get quite a bit of intraplate volcanism because it's not really a plate boundary. It's these intraplate earthquakes that are responsible for the largest earthquake in the U.S., the largest reported earthquake. So this is in 1811, the early 19th century. This is the New Madrid Fault Zone, right along the borders of Missouri, Arkansas, Tennessee, and Kentucky. There's a little town there called New Madrid. And in 1811, there was a reported earthquake that's been estimated at 8.2 on the Richter scale. That would be the largest earthquake to ever occur in the U.S. that's actually been recorded. And this actually occurred on a failed rift. And so when Pangaea, the supercontinent of Pangaea, was formed, it started to separate when Africa and Asia started to pull, and Europe started to pull away from North America and South America and to form the Atlantic Ocean. And as it started to do that, it actually tried to separate here in around the New Madrid area. So this is a failed continental rift, but because it's tried to rift here, there's a lot of pre-existing faults now and fractures, and they're still kind of reworking their way out. And so there's a lot of accommodation that's going on, and that's why you can see that even though we're far away from a plate boundary, we have this interesting little hotspot of earthquake activity that occurs in this New Madrid fault zone. There's reports that the Mississippi River actually flowed backwards after this earthquake occurred. There's also quite a few intraplate earthquakes that occur in places where there were large ice sheets. So for example, Canada has these sporadic earthquakes. They tend to be small, relatively shallow earthquakes, but this is believed to be a result of the accommodation as the crust is rebounding back up after having a huge laurentide ice sheet on it. We'll talk about these ice sheets a little bit more when we talk about the recent history of the climate. And that giant mass of ice, multiple kilometers thick, as it receded, all that mass was removed off the crust, and so the crust is essentially rebounding back up, and as it does that, it's accommodating itself through earthquakes and shaking. Some of the hazards that are associated with earthquakes are obviously landslides and avalanches. Anywhere you have a steep surface or a steep slope and you start to shake the ground, those areas are already inherently weaker because gravity is pulling them down the slope. If you can overcome the friction that's holding the slope together, you can start to have big slides. This is very common, for example, in California during earthquakes. We have a coastal mountain range that's relatively close to the San Andreas Fault. In fact, it kind of hugs the San Andreas Fault. And there's some relatively steep slopes there. And so one of the hazards that occurs anytime California has an earthquake is that we have quite a few landslides. Sediment liquefaction is one that we just touched on a little bit, but this is where we have very rich water-filled sediments, and when the shaking occurs, that water actually works its way towards the surface, and as it works its way towards the surface, it turns a solid surface essentially into a liquid. Here's an image from the Japan earthquake in 2011 where you can see the water seeping out of the cracks of the ground. This is, long after the shaking has already subsided. You can see the people kind of exploring and checking out all this water that's seeping out onto the ground. The ground is still solid enough there that they're not in any danger. But if the ground becomes weak enough, then you can start to have serious effects on infrastructure. Vehicles sink into the ground, full buildings sinking into the ground. In fact, Japan is very prone to liquefaction, and in places like Nagita, you can have entire buildings start to sink. or entire building complexes tip over and sink down. So these buildings not only sank about a whole story down, but they also just tipped over. You can see there's not a lot of damage from the actual earthquake itself. The buildings aren't collapsing by any means. The structure is sound, but the fact that the foundation became liquid, the foundation that the building was built on, the ground, essentially liquefied, these entire buildings just topple over. And so this becomes a major hazard in certain areas. Fire is a major hazard. So a lot of times what happens is that the shaking breaks things like gas lines that can ignite fires, but it also breaks a lot of water mains, which makes putting fires out very difficult. So this was an image of the Northridge earthquake in 1994. This is a mobile home park in Sylmar, and this is exactly what happened there. The water mains broke, some gas lines broke in certain houses. So you had a few fires erupt, but when firefighters reached the scene, they could only use the fire that they had in the truck because the fire hydrant mains were all broken. And so they didn't have access to water. And in fact, this is what happened in 1906 in San Francisco. The earthquake itself did quite a bit of damage to the city. You can see these facades that are broken down and the bricks in the middle of the city. But about 80% of the city was relatively undamaged. 20% was pretty severely damaged. There was a smaller amount that had some minor damage, but the structures were relatively wood. The bricks on the outsides were just the facades, and so it was mainly cosmetic. Obviously, if you're standing below one of these facades that comes down, that could do some terrible damage. But in general, the city survived the earthquake pretty well. It was the fire that happened for 3 days after the earthquake that really demolished the city, and then something like 85% of the city was essentially burned to the ground. And again, the same thing was occurring. Any access to water was severely restricted by the shaking. All these water mains were breaking, and obviously in 1906 our firefighting capacity was different and our technologies were different, but it was really the fire that ravaged San Francisco in 1906. We also have issues with things like disease outbreaks. So this is an image of Haiti in 2010. Remember, this is only a 7.0, but you can see how much damage there is. A lot of this is due to the lack of use of rebar in the cement. Rebar are the metal rods that you see being laid down when people pour cement. Cement is really strong in a compressional sense. You can stand on it and won't break much at all. But when you pull on it a little, tensile strength, it actually is relatively weak. And so because earthquakes have pushing and pulling and side-to-side motion, or any sort of concrete without rebar in it is really easily broken. And so that's one of the reasons that we put rebar into our concrete, is to strengthen it primarily for tensile strength, not really for compressional strength. In Haiti, their building restrictions were pretty limited. It's a developing country. And what happened was so much of the buildings were built without rebar that there was a huge amount of devastation due to a relatively small earthquake, only a 7.0, very similar to the Loma Prieta earthquake that I talked about at the very beginning that I experienced in 1989 as a young boy, that only killed 63,000 people. The Haiti earthquake is estimated to have killed over 300,000. And it was the direct shaking and the collapse of the buildings that led to a good chunk of that, but quite a bit of that was also attributed to weeks after there was no access to sanitation, there was no access to clean drinking water. You had cholera outbreaks and starvation issues, and so there's a lot of infrastructure that can get damaged, and so there's these secondary effects and secondary hazards that can occur when you have large earthquakes like we did in Haiti in 2010. Earthquakes can also create tsunamis. So tsunami is a Japanese word. It means harbor wave. This has nothing to do with tides. This gets confused with tidal waves. We're going to spend a whole chapter talking about the oceans and tides, but this has nothing to do with tides. It's named a harbor wave in Japan because Japan has a lot of harbors along its Pacific coast, and the harbors tend to amplify the waves. But these are usually waves that are created from the displacement of the seafloor. So these are earthquakes or submarine landslides or even submarine volcanoes. And what happens is when the fault displaces all that rock, it also displaces all the water above it, and it creates this giant mound of water, and that mound of water starts to move in every direction. And as it moves at the speed of essentially a jet airliner. And you can see that out in the open ocean, the tsunami wave is relatively small. Some people don't even notice. But as it approaches shore, it starts to stack up and it starts to get much higher. And this was what created a lot of the devastation in Sumatra in 2004 and in Japan in 2011. Tsunami waves are very different than wind waves, primarily in the fact that they have a very long crest to trough, or very long wavelength. So on the left, those are standard wind waves that we see lapping up when we go to the ocean. Sometimes they could be very big. We've seen big surfing events, maybe from northern Hawaii or from the North Shore of Hawaii pipeline and things like that. You can get these waves can be pretty massive, but they are relatively short in their wavelength. The wave comes, it breaks, and then the next one's coming just a few seconds after that one. What happens in a tsunami wave is that the wavelength is huge. And so you don't really get a big wave that crashes on shore. You may get some wave action at the beginning, but really what happens is the ocean just infiltrates onto land and continues to move onto land and essentially wipe out anything in front of it. This is an example of the tsunami that hit Sumatra. So one devastating thing in Sumatra was this was the day after Christmas, December 26th, known as Boxing Day. And this was a 9.0 earthquake, and it created a tsunami that was on the order of 15 meters high. So we're talking about the height of something like a 4-story building. And the image on the right there, these are tourists. So a lot of people will go to Indonesia during Christmas to get away from the cold and enjoy Christmas on the beach. And because the first wave was actually pulling away from shore, what it did was it exposed a lot of the reef and a lot of the tide pools that the people hadn't seen in the prior few days that they had been there. And so that brought a lot of people down to the beach. And thankfully, some of the locals started to realize what was happening and started yelling at people. But you can see these folks running and the giant waves that are moving onto shore. The earthquake in Sumatra wasn't really the main loss of life at all. It was really the tsunami that was responsible for the over 250,000 people that lost their life. Here's some images of the tsunami that hit the Tohoku after the 2011 Tohoku earthquake. Again, another 9.0. You can see that what used to be a city with this barrier island, not only is the city gone, but it dramatically affected the coastline. It removed so much sediment and things that barrier island is essentially gone. You can see how far back the water went into these little crevices and around the mountains. And so this was, again, one of the devastating things in the 2011 Tohoku earthquake, but Japan has really good warning systems and very good infrastructure. And so actually the loss of life in Japan is under 30,000 from a 9.0 earthquake, because they had warning sirens going off, warning people to get to higher ground before the tsunamis reached in most towns. And they have really good engineering practices for their buildings. So most of the buildings survived the 9.0 earthquake. We really want to study this stuff so that we can figure out how to mitigate loss of life. So we really want to figure out earthquake prediction. And what we can say about earthquake prediction is that we're good at making long-term predictions. We can say that there is going to be a high chance of a magnitude 7 in San Francisco over the next decades or century. What we're not good at is making short-term predictions, real-time predictions of saying, hey, tomorrow we got to get everybody out of San Francisco Bay Area because there's going to be a really big earthquake. And that's the part that we'd really like to have. That's the holy grail for earthquake prediction, is being able to predict in real time. But unfortunately, it's something that we can't do very well yet, because a lot of times we get the main shock, for example, before we get any foreshocks. And so it's that main shock that surprises us, and we know the recurrence interval of the stick-slip behavior. So we're good at making these long-term predictions, but we don't necessarily know when the forces will overcome the friction of the fault. One way that we work with this is that we figure out earthquake preparedness through engineering. We're pretty confident we're not going to be able to get everybody out because we just don't have our prediction capability good enough. But we can start to build our buildings that they're strong enough such that they can withstand the different types of surface waves. We can retrofit buildings that already exist. We literally put the foundations on rollers and springs that dampens the shaking from the surrounding land. We can put buoys out in the ocean to monitor for tsunamis, so we know that when there's a tsunami coming, and we can have good evacuation routes and get people out. And so, until earthquake prediction gets better, we're going to really have to rely on our engineering practices to help mitigate the loss of life. But in the Western world, where we have, pretty high building practices and high building standards and regulations, we really have mitigated the loss of life from things like earthquakes pretty dramatically. However, in the developing world, that's still an issue. And the fact is that it's not a matter of if, but rather when. So the population of the San Francisco Bay Area last year actually went down a little bit, but it's sitting at somewhere around 7.5 million. And so there is a active fault zone that is accommodating the motion between the North American plate and the Pacific plate there. We call it the San Andreas Fault, and it will rupture again. And that's just a matter of a matter of when, not if. And so we really need to be prepared in order to mitigate loss of life and to have the buildings withstand this type of shaking, because we know it's going to happen again. We're measuring the plate motion. The plate motions are continuing to happen, and the fault has been locked. And so there's definitely this energy is building up, and at some point it's going to overcome the friction on the fault, and we're going to have another earthquake. Well, thanks for listening. I hope you guys enjoyed this lecture in the Introduction to Earth Sciences lecture series. Please share it with anybody that you know. I'm going to put these out for free. We'll have about 19 parts, and hopefully you have a nice introduction to Earth Science. Again, please follow me at Matthew Wielicki on Twitter and subscribe to my Substack, noclimateemergency.substack.com. Thanks again for listening, and have a great day.